In this video, we're going to think about hydroboration-oxidation from the perspective of synthesis, hopscotching straight from the reactant to the product, only keeping in mind some of the details about the reaction that you would learn from the mechanism. So for example, there's another video that animates this mechanism for you in just about 1 minute and 40 seconds and notes where these are coming from. The boron and one of the hydrogens in borane, that's pH 3, they add at the same time. Hydrogen is less bulky than the boron is, and so it adds to the more substituted position that is anti-Markovnikov. So in this reaction, you're going to have anti-Markovnikov addition. Hydrogen will go on to the more substituted carbon because it is the less bulky of the two things you're adding. So you add hydrogen and boron, that's hydroboration, and then you replace the boron with an oxygen, one of the oxygens in this H2O2, hydrogen peroxide, and that's the oxidation. So you add hydrogen and boron, and then you replace the boron with an oxygen. So hydroboration, oxidation. Now this pH 3, borane, is not the funnest thing to work with. It's a really toxic compound, and if you have to deal with a toxic compound, which preferably you never will, but if you have to deal with a toxic compound, it's best to deal with a solid. It's much easier to contain a solid. Liquids, okay, just make sure you use it under a fume hood because every liquid is constantly evaporating. And then gases are the trickiest because gases are very hard to contain. So borane is toxic and it's a gas, so it's not the best thing to work with. A better option is 9-BBN. Now, this is a bicyclic compound. You're not responsible for knowing what this looks like, but I'll show it to you here. So it's a big compound, a 9-membered ring. It's called 9-BBN, and that stands for 9 bora. That's for the boron. Bicyclo. And then you have 3 carbons on one side, 3 carbons on the other side, 1 atom, the boron going up, nonane. So you have 9-BBN, 9 bora bicyclo 331 nonane. Notice that it still has the hydrogen and the boron. The hydrogen is the less crowded place, so it'll go to the more substituted carbon. The boron is in a really crowded place, so it'll go to the less substituted carbon. And this will come back again in the next chapter on alkynes. 9-BBN will have a particular use. But for now, we can recognize it as maybe a safer alternative to borane. If you use 9-BBN, you would still want to use tetrahydrofuran, THF, to stabilize it. The THF there, tetrahydrofuran, which looks like this, is an unreactive compound that uses its lone pairs to stabilize an empty p orbital on the boron. The boron has 3 bonds, 0 lone pairs. That means it's trigonal planar. That means it's sp2 hybridized. If it's sp2 hybridized, then you have one of the p orbitals that is just sitting there empty, and that makes that very reactive. So the THF sort of lends its lone pair there to help stabilize that compound. Okay, well there's a whole video on the mechanism for this, but I wanted to note that it's anti-Markovnikov because the boron is more bulky than the hydrogen, so it adds on the less substituted position, and because they both add at the same time, they're both going to add on the same face of the molecule, and that's called syn addition. So if you notice you're adding an H and an OH, just like you have up here, but notice they're both going in the same direction, they're both coming out at us. The fact that they added on the same side of the double bond is syn addition. Okay. Now you don't get rearrangements with this either. So all we have to do, you'd look at the reaction, you'd say, double bond. And you'd think about addition reactions. Okay, what are we going to add? You look at the recipe, you see boron and hydrogen, so hydroboration, and then oxygen that you're going to replace the boron with, so hydroboration-oxidation. Now you'll want to know all of these recipes from scratch. You'll want to be able to write them down, but right now we're just recognizing them and drawing the product that we get from them. So if you have hydroboration-oxidation, you're going to be adding H and OH, and you're going to do it in an anti-Markovnikov and syn way. So the first step is just adding or drawing the carbon skeleton. None of the sigma bonds are going to change. It's just the pi bond that's going to get used up. We're going to use the pi electrons to help stick stuff onto this molecule. Okay, well, it's anti-Markovnikov. So we have to think about which carbon. That means the hydrogen is going to go to the more substituted carbon. This carbon on the left is bonded to 1, 2, 3 other carbons, so it is tertiary. The carbon on the right is only bonded to one other carbon, so it is one other carbon, so it's primary. So the tertiary carbon is the more substituted carbon. And so because this is anti-Markovnikov, that is where the H is going to go, the more substituted carbon. That means the OH will go on the other carbon, because we don't have to worry about rearrangement, and that's your product. And we just want to make sure that they're both adding on the same side. In this particular case, it doesn't matter because neither of our carbons are chiral centers, but why not, just for the sake of consistency, I'll draw them both going on the same side. Now, if those were chiral centers, we'd also want to draw the enantiomers. That would be, the enantiomer would be the same molecule, but where both of them are going away. In this case, though, these two molecules are the same. You can sort of rotate this like that, and you'll end up with this molecule here. Okay, so that's hydroboration-oxidation. All right, we'll do that again. So we have an alkene. You see an alkene, and instantly you should think addition reaction. What am I adding? You look at the recipe. Boron and hydrogen, hydroboration. We're going to replace the boron with an oxygen from hydrogen peroxide, so that's going to be hydroboration-oxidation. With hydroboration-oxidation, you're adding H and OH, and it's going to be anti-Markovnikov. And it will also be syn. So we can redraw the skeleton, the sigma bonds exactly as they are, just no pi bond. We have to think about the more and less substituted carbon. This carbon on the left is bonded to 1, 2, 3 carbons, so it's tertiary. The carbon on the right is bonded to just one carbon, this carbon here, so that is primary. Because it's anti-Markovnikov, the hydrogen will go on the more substituted carbon. So that'll go there. That means the OH goes on the other carbon because it's anti-Markovnikov. There's no rearrangement. And they're syn. Now we don't have any chiral centers forming here, but just to emphasize the fact that they're syn, I'm going to have them both adding on the same face of the double bond. If there were chiral centers, you would want to include the enantiomer. That would be where they're both going away. But here it would be wrong to say plus the enantiomer because there are no chiral centers, so you can't have an enantiomer. Okay, so we do that same thing with this next one. You look at the reagent, you see an alkene. When you see an alkene, you should think big category addition. We're not going to do substitution or elimination, we're going to do addition with that. Well, what are we adding? We're adding a boron and a hydrogen, so that's hydroboration, followed by an oxygen that's going to replace the boron, an oxygen from hydrogen peroxide. And so that's oxidation. So hydroboration-oxidation. With hydroboration-oxidation, you add an H and an OH. It's anti-Markovnikov, and it's syn. So start by drawing the same sigma bonds. The carbon skeleton stays the same, it's just the pi bonds, the pi electrons that we're going to change. Because this is anti-Markovnikov, we need to know which carbon is the more substituted one. The carbon on the left here is bonded to 2 carbons, so it's secondary. The carbon on the right is only bonded to 1 carbon, so it's primary. Because this is anti-Markovnikov, the hydrogen is going to go on that secondary, that more substituted carbon. That means that the OH goes on the other carbon in the double bond. We just have to make sure they're syn. Now we didn't form a chiral center here, so technically we don't have to include the stereochemistry, but I'm going to just to emphasize the fact that they add on the same side. So they're either both going to be coming out at you, or they could also be both going away. Here we don't have any chiral centers, so we don't have to draw two enantiomers. Notice I'm also drawing the hydrogens in here, which you are more than welcome to do. It would also be correct if you don't draw those hydrogens, because they're implied in these skeletal structures. So these are really the same thing, same molecule, and both of them are correct here. You don't have to draw this three-dimensional arrangement in this particular molecule, because this is not a chiral center. It has two hydrogens on it. It's only bonded to three different things, not four. Okay. Exercise 919 is the same thing. We're going to do hydroboration-oxidation. So you'd look at the carbon chain and you'd say, okay, an alkene. The big category I want to think in is addition, right? In order to do substitution or elimination, you need a leaving group. We don't have that here. We have a pi bond. Pi bonds allow you to do addition. So what are we adding? You look at the recipe. We're going to add boron and hydrogen. That's hydroboration. And then we're going to replace, and they'll add on the same side, syn, of the double bond. And then we're going to replace the boron with one of the oxygens in hydrogen peroxide. So that's oxidation. So we're doing hydroboration-oxidation. Hydroboration-oxidation, you add H and OH, anti-Markovnikov, and syn. So you can redraw that carbon skeleton. We need to add the hydrogen on the more substituted carbon. This carbon on the top is bonded to 1, 2, 3 other carbons. That makes it tertiary. The carbon on the bottom is bonded to 1, 2 other carbons. That makes it secondary. Because this is anti-Markovnikov, we're going to add the hydrogen to the more substituted carbon. And that means the OH will go on the less substituted carbon. Now, in this case, we do have a chiral center that we formed. So, the two places where you'd have to look are the two carbons that have the things we added on them. This carbon at the top, with the hydrogen on it, is bonded to 4 different things. It has a part of the ring with no OH on it. In the other direction, it has a part of the ring with an OH on it. It has a methyl group, and it has a hydrogen. So that's 4 different things. Further, the other carbon that has the OH on it is also a chiral center. It has an OH. It has a part of the ring with a methyl group on it. It has a part of the ring with no methyl group on it. And it has an implied hydrogen. So that's 4 different things. That is also a chiral center. So there are 2 chiral centers in this molecule. So we just have to draw the 2 possible enantiomers we could get. Oops. Well, we know that the H and the OH add syn. So either they both add coming out at us, or they both add going away. Those are the only 2 ways they could add to this molecule. So we just want to make sure that those tetrahedral carbons are drawn correctly. A correctly drawn tetrahedral carbon will have 2 bonds in the plane, one coming out at you and one going away. So if we're looking at this top one, you already have 2 in the plane, one coming out at you. That means the methyl group here would be going away. For the bottom one, 2 in the plane, one coming out at you. We could have the hydrogen going away, and actually we could just erase that. I mean, if you want to, you could draw it in, but because you have a skeletal structure, it could just not be there. So you may see it like this, for example, in a solutions manual, or if you were taking a standardized test that was multiple choice, you might see it like that. On the other hand, in the other molecule, for this top carbon, chiral carbon, if you have 2 bonds in the plane, one going away, that means that this methyl group must be coming out at you. And for the bottom one, you'd have 2 bonds in the plane, one going away, so the hydrogen would have to be coming out at you. Now you could just erase it, or you could draw it coming out at you, either way. You could erase the hydrogen because it's a skeletal structure, so it's implied. So those would be the two products you would get, and it would be a racemic mixture of those two. And the reason is because our original molecule, the alkene, this carbon has 3 bonds, 0 lone pairs, so it's trigonal planar. This carbon has 1, 2, 3 bonds, 0 lone pairs, so it's trigonal planar. Alkenes are trigonal planar, so they're flat. So this, when the boron and the hydrogen land on it, it could land on each side with equal probability. So it could land on the top and give you this product, or it can land on the bottom and give you the other product with equal probability. So that'll be a racemic or 50-50 mixture of those two enantiomers. Okay, so with B, we're going to do the same thing. You see an alkene, and you see a pi bond, and you think, okay, addition reactions. What are we adding? You see borane and THF, followed by, so hydroboration, followed by hydrogen peroxide and sodium hydroxide. So replace the boron with an oxygen, that's oxidation. You see the recipe for hydroboration-oxidation. So you know that you're going to be adding, you know that you are going to be adding H and OH, anti-Markovnikov, and syn. Now that's only going to affect the pi bonds, so the sigma bonds will all be the same. So you can redraw the molecule with all the same sigma bonds, just don't include the pi bond. Okay, it's anti-Markovnikov. That means the H, the hydrogen, has to go to the more substituted carbon in the double bond. This carbon on the left is bonded to 1, 2, 3 other carbons, so it would be tertiary. The carbon on the right is bonded to 1, 2 other carbons, so it's secondary. Because it's anti-Markovnikov, the hydrogen is going to go on that more substituted carbon. And that means the OH goes on the other carbon. So there's your anti-Markovnikov addition. Now we just need to think about chirality and syn addition. Well, we have two possible places where we could have a chiral center. We could have one where the hydrogen added, or we could have one where the oxygen added. Those are the only two carbons that changed, that could have become chiral. The carbon where the hydrogen added, has two branches that are the same. Either way you go around that ring is the same. So it's really only bonded to 3 different things. The ring, the hydrogen, and the straight chain. So that carbon is not chiral. Oops. The other carbon, however, is. It has the OH, it has a methyl group, and it has this crazy ring. In addition to that, it has an implied hydrogen. So that carbon with the orange star is a chiral carbon. And that means we're going to have to draw both enantiomers of this product. Okay, well, we know that we could get syn addition. That means that because it's syn addition, the hydrogen and the oxygen will either both be coming out of us, or they will both be going away. So those are the two possible products we could get here. It's going to be a racemic mixture of the two because the alkene was trigonal planar. The carbons in the alkene are trigonal planar, so it's flat, and the borane can land on either side of it with equal probability. And the boron just gets replaced with the oxygen to give you your product. So these are our two possibilities. We just need to make sure everything is drawn okay. If you have a tetrahedral atom, like we do at these chiral centers, you want to make sure you have 2 bonds in the plane, one coming out and one going away from you. And we can make the bond to the hydrogen going either out or away. At the top, it would have to be going away. At the bottom, it would have to be coming out. And that makes sure that you have 2 bonds in the plane, one coming out and one going away. 2 bonds in the plane, one coming out and one going away, so that it's tetrahedral. Technically, though, you don't even have to include those hydrogens because this is a skeletal structure, so they're implied. That goes for the other hydrogen as well. And so these are your two possible products for this hydroboration-oxidation. If you did this reaction, you would get both of those in a 50-50 mixture. Okay, C. You see an alkene. Alkene should make you think big picture addition reactions. Those are the types of reactions you can do with a pi bond. What are we adding? You'd look at the recipe. You'd see a boron and a hydrogen. That's going to be hydroboration. The boron gets replaced by an oxygen, so that's oxidation. Hydroboration-oxidation. So if you see two steps, borane and tetrahydrofuran, followed by hydrogen peroxide and sodium hydroxide, it is hydroboration-oxidation. Hydroboration-oxidation adds an H and an OH across the double bond. It does it in an anti-Markovnikov way, and the addition is syn. So only the pi bond is going to be affected by this. All of the sigma bonds stay the same, so you can redraw the carbon skeleton just without the pi bond. And because it's anti-Markovnikov addition, we need to know which carbon in the pi bond is more substituted. This carbon here is secondary. The other carbon is primary. So the hydrogen is going to go to the more substituted carbon. That's the carbon there. That means that the OH adds on the less substituted carbon, the other carbon in the double bond. Okay, so that's our a possible product. We just have to make sure it's syn addition. We could easily make these just solid wedges. They added on, the H and the OH add on the same face of the double bond. If we have a chiral center, then if we form a chiral center, then we have to draw the enantiomer. So let's see if we do have a chiral center. And here we don't, because this carbon here is bonded to another hydrogen. That means it's only bonded to 3 different things. So we could just erase those hydrogens. They're implied in this skeletal structure. And the carbon on the end is bonded to 2 hydrogens. So again, it's only bonded to 3 different things. And so really, we don't even have to say the stereochemistry for that bond because it's not a chiral center. So whether it's pointing out at us or going away from us, it's the same molecule. And so that is our only product for this hydroboration-oxidation. Okay, let's try D. You see an alkene, you think addition reactions. You see borane, BH3, in THF, stabilized by tetrahydrofuran. That's the first step, followed by hydrogen peroxide and sodium hydroxide, and you think hydroboration-oxidation. You add hydrogen and boron, and then the boron is replaced by oxygen. So with hydroboration-oxidation, we're going to be adding H and OH, anti-Markovnikov, and syn. So you redraw the carbon skeleton exactly as it is. This will only affect the pi bond. It won't affect the sigma bonds at all. And we're going to add H and OH, anti-Markovnikov. Because it's anti-Markovnikov, we have to know which carbon in the double bond is more substituted. The carbon on the right is bonded to 3 other carbons, so it's tertiary. The carbon on the left is only bonded to 2 carbons, so it's secondary. So because it's anti-Markovnikov, the hydrogen goes to the more substituted carbon. That's the tertiary one. And that means that the OH goes on the other carbon in the double bond. Okay, so we just need to make sure that those add syn. Now I've been drawing them all coming out at us. We could also draw them going away. So this is one possibility. We just have to think about whether we formed a chiral center or not, because if we did, we have to draw the enantiomer. You could have racemic mixture, a 50-50 mixture of the 2 enantiomers with hydroboration-oxidation because the original alkene was flat. Okay, well, the carbon with the hydrogen is not, these are the only 2 carbons that could be chiral centers here. The one with the hydrogen is not chiral because it's bonded to the same thing twice. It's bonded to 2 methyl groups. That means that carbon can only bonded to, at most, be bonded to 3 different things. So it has 4 branches, but only 3 of them are different. So that's not a chiral center. The carbon on the left is bonded to an OH. Let me actually move that over. The bond is to the oxygen, and OH to this sort of isopropyl group, to an ethyl group, and to an implied hydrogen. Notice that the hydrogen would have to be coming out at us because we already have a bond, two bonds in the plane and one going away. So the next one would have to be coming out. So that's bonded to 4 different things. So that is a chiral center. And so we just have to draw the enantiomer. Now, the enantiomer means that the oxygen and the hydrogen, the OH and the H, would have added on the opposite side. So say both coming out at us. And that means this other hydrogen would have to be going away. Now technically, this is perfectly right. I wouldn't take any points off for that. This is a racemic mixture of those two things, 50-50, mixture of those two products. But because it is a skeletal structure, you don't have to draw these hydrogens in. And so those would be a racemic mixture, the two products you'd have as a racemic mixture in this reaction. Okay, so let's do this next one. You'd look at the reactants, you'd see an alkene. That means you're going to do an addition reaction. That's what alkenes can do. Those extra electrons, that extra molecular glue in the pi bond can be used to stick new stuff onto that molecule. What are you going to be adding? You look at the recipe. You see borane stabilized by tetrahydrofuran, followed in a separate step by hydrogen peroxide and sodium hydroxide. That means you're going to add hydrogen and boron, so hydroboration, and then you'll replace the boron with an oxygen, so oxidation. Hydroboration-oxidation. Well, for that means in hydroboration-oxidation you're going to add H and OH, anti-Markovnikov, and syn. So you can redraw the original molecule just without the pi bond. We're going to use those pi electrons as molecular glue to stick new stuff onto the carbon skeleton. The sigma bonds all stay the same, and because it's anti-Markovnikov, we want to add the hydrogen on the more substituted carbon. And the carbon here on the right in the double bond is bonded to 2 other carbons, so it's secondary, and the carbon on the left is bonded to just 1, so it's primary. So we're going to put the hydrogen on the more substituted carbon, the secondary one. And that means that the OH ends up adding on the less substituted carbon. Now, they add syn, so you could give the chirality here. You could say, the stereochemistry, you could have them both either coming out or going away, but the truth is neither of those carbons are chiral centers. And so you don't have to give the stereochemistry. No matter which way those atoms are pointing, it's the same molecule. And so this is a perfectly valid structure for that product. Notice you also don't have to write in the hydrogen because it's implied in the skeletal structure. Okay, so let's do F. In F, you see an alkene, and that means addition reaction. You're going to use those pi electrons to add something onto the molecule. What are you going to add? You look at the recipe. You see borane stabilized by tetrahydrofuran, followed in a separate step by hydrogen peroxide and sodium hydroxide. That means you're going to add a hydrogen and boron, so hydroboration, and then replace the boron with an OH, with an oxygen, so oxidation. So this is hydroboration-oxidation. When you do hydroboration-oxidation, you add a hydrogen and an H and an OH. You add them anti-Markovnikov and syn. So you can redraw the carbon skeleton with all the same sigma bonds. We're just going to use the pi bond to stick new stuff on here. And we need to know which carbon is the more substituted carbon in the double bond because that's where we're going to put the hydrogen. The carbon on the left is bonded to 3 carbons, so it's tertiary. The carbon on the right is bonded to 2 carbons, so it's secondary. Because it's anti-Markovnikov, we're going to put the hydrogen on the more substituted carbon. That means that the OH will go on the other carbon. So that is one possible product. Now it is adding syn, so if you want, you can draw in the bonds. You just need to make sure they're pointing in the same direction, either both coming out at you or both going away. And you have to check to make sure you don't have a chiral center, because if you have a chiral center, you want to draw both enantiomers. And here we actually have two chiral centers. Both of those carbons are bonded to 4 different things. The one on the left where the hydrogen added, that's bonded to a methyl group, a ring, a straight chain with an OH on it, and a hydrogen. So that's 4 different things, so that's definitely chiral. And second, the other carbon with the OH on it, that is chiral too. That has an OH, it has a methyl group, it has a weird chain with a ring, and the 4th thing is an implied hydrogen, which notice would have to be going away in order to keep that as tetrahedral. So we need to make sure that we draw the 2 enantiomers. We're not quite done drawing this enantiomer. This one is tetrahedral on the right because it has 2 bonds in the plane, one coming out and one going away. We need to do that same thing for the carbon on the left. It has 2 bonds in the plane, one coming out. We just need to make that last methyl group go point away. So that's one enantiomer. And then we can get the other enantiomer if we switch the configurations. That means this hydrogen would be going away. The methyl group would be coming out. The hydrogen here would be coming out at us. And the oxygen would be going away. The OH would be going away. That hydroxyl group would be going away. And so those are your 2 enantiomers, and you'd have a 50-50 or racemic mixture of those 2. Now, technically, you can erase the hydrogens. Those are implied in these skeletal structures. And so this is also a completely valid way of drawing the 2 products you would get with this hydroboration-oxidation reaction. Notice that, and this is sometimes confusing for students, notice that what is syn is the H and the OH. Those are what are syn. Here, you have an oxygen pointing out, and the implied H is also pointing out. The methyl branch that was there before, that was not added onto the carbon chain, that's going away. So don't confuse this with anti. Those are going in opposite directions because the OH and the H are syn. Okay. One last way of talking about hydroboration-oxidation is with this naming. So let's try to name this, to draw this molecule's name, and then go through the steps for hydroboration-oxidation. So first, start by drawing the backbone. Here we have 3-hexene. Now if you're drawing a double bond that has stereochemistry, start with a double bond. So start by drawing this double bond here. And actually, this is going to be on carbon 3. That means it'll go to carbon 4. We know it has to go to 5 and 6. And we also know that it needs to go to 1 and 2. But will it go up 1 and 2, or will it go down 1 and 2? That's where you look at the stereochemistry. Here it's E, that stands for opposite, right? Or entgegen in German, which means opposite. It's E as opposed to Z, which is if they're on the same side. Coming from the German zusammen, which means together. Okay, well here it's opposite, it's E, that means you want 1 and 2 to go on the opposite side as 5 and 6. So you could see how this branch is going down, this branch is going up. If you had a dotted line through the long end of the double bond, these are on opposite sides of that line. So that's E3-hexene. We have one other branch here. It is 3-methyl. So we want to put a methyl group on carbon number 3. Okay, that is our alkene. quick review of naming alkenes and E and Z naming. Now if you do hydroboration oxidation to this, you're going to get rid of that pi bond, and you want to think about where the hydrogen will add. It will add to the more substituted carbon. The one on the left is tertiary, the one on the right is secondary. So the hydrogen will add to the more substituted carbon. The OH will add to the less substituted carbon. Finally, we do have chiral centers here, so we just want to draw both enantiomers. We'll have one where the OH and the H are coming out, and another one where the OH and the H are going away. Oops, sorry. One where they're coming out. So they added syn coming out, and one where they're going away. You just want to make sure that these bonds are tetrahedral, so these two chiral centers should have two bonds going in the plane, one coming out and one going away. That means that this methyl group needs to be going away, and this ethyl group, or the hydrogen in this other case, is going to be going away. And here, the methyl group needs to be coming out, and the hydrogen here will be coming out. So those are your two products. You can erase the hydrogens because they're implied in the skeletal formula, and that gives you your racemic mixture of these two products. So those are the two products you'd get if you did hydroboration oxidation with E3-methyl-3-hexene. Okay, so hopefully this rather extended video will have helped you with predicting the products of hydroboration oxidation reactions. Make sure you know the recipe, you're able to write that recipe down from scratch, and just keep in mind it's anti-Markovnikov and syn. And if you form a chiral center, you want to show that you get a racemic mixture of the two enantiomers.